For generations, extreme engineering was defined by American ambition. Structures like the Hoover Dam stood as absolute monuments to 20th century progress, proving that sheer will could conquer nature. The Golden Gate Bridge became a global icon, setting the standard for how nations connect their people across previously insurmountable gaps. But today, that legacy is fracturing. Currently, 42% of all bridges in the United States are dangerously past their engineered lifespans, costing the economy trillions as vital arteries slowly decay. The breaking point for this global divergence arrived in 2008. That year, the U.S. promised a $33 billion high-speed rail line connecting Los Angeles to San Francisco. Decades later, that project sits as isolated concrete viaducts, stalled and ballooning past $128 billion. In that exact same year, on the other side of the world, China launched the Beijing-Tianjin high-speed line. From that single line, they rapidly expanded. Today, China operates over 40,000 kilometers of high-speed track, enough to wrap entirely around the Earth's equator, with trains running at a blistering 421 kilometers per hour. This chart shows the stark economic reality making this possible. For the exact amount of money the United States spends to lay a single kilometer of track, China builds 5. While Western megaprojects are now consistently measured in decades of delays, China has turned complex engineering into a standardized routine, effectively collapsing geographical distance by turning multi-day journeys into 3-hour commutes. That same speed applies to marine architecture. Right now, 8 of the 10 longest sea bridges on the planet are located in China. In the United States, planning and constructing a standard highway bridge requires an average timeline of 7 to 10 years of heavy disruption. Chinese engineers bypassed these delays by inventing advanced pivot technology. They prefabricate massive sections parallel to the terrain and then smoothly rotate them into perfect alignment over deep gorges or active highways. Using this method, they rotated a 16,000-ton bridge section into its final position in just 90 minutes. In Hebei province, they broke that exact record, locking an entire span into place in 85 minutes. By treating megastructures like factory products, they proved that multi-year public disruptions are a byproduct of outdated construction methods rather than a physical necessity. We can see the results of this methodology in the 55-kilometer Hong Kong-Zhuhai-Macau Bridge, a megastructure fortified to withstand extreme typhoons and direct impacts from 300,000-ton cargo ships. But the real challenge lay hidden below the surface, where engineers had to sink 33 individual tunnel tubes to the seabed. Each one weighed 80,000 tons and stood 8 stories high. This schematic illustrates the precision required. Lowering massive concrete boxes through chaotic currents was like threading a needle, maintaining a 5-centimeter margin of error. To prevent sinking, they chemically hardened the soft sea sediment into a locked, rigid grid capable of holding millions of pounds. Even with that preparation, the ocean fought back. In 2017, severe underwater currents forced 2 massive tunnel sections 3 centimeters out of alignment, threatening to collapse the entire multi-billion-dollar project. Instead of abandoning the drop, the crew deployed a custom dynamic hydraulic system. In just 15 minutes, they pushed millions of pounds of concrete back into perfect millimeter alignment against the flow of the ocean. The success of this tunnel proves that even in unstable deep-sea environments, hydraulic correction systems can now manage massive loads with millimeter accuracy. For centuries, taming water through hydroelectric dams has been a primary symbol of national capability, a standard set early on by the Hoover Dam. The Baihetan hydropower station functions as a subterranean world carved directly into the mountain. Compare this subterranean work with the Boston Big Dig, an infamous American underground project plagued by surface chaos, structural leaks, and a 220% budget overrun. Behind Baihetan's concrete face lies a network of internal tunnels stretching 217 kilometers, the equivalent distance of stacking 300 Empire State Buildings end to end. Looking at this wireframe of the main power cavern, we can see the volume of the excavation. At 438 meters long and 90 meters high, the underground hall is large enough to park 13 Boeing 737 airplanes. Despite the complexity of hollowing out a mountain, the station was delivered on time. Today, it generates 3 times the electricity of the Hoover Dam. Baihetan represents a masterclass in project delivery. It proves that mountains can be utilized as power stations for millions of homes, precisely on schedule. These high-speed rails, sea bridges, and megadams are the result of a systematic approach to civil engineering that prioritizes speed and prefabrication. By combining these technologies with vast logistical resources, China has claimed the mantle of the world's primary infrastructure power. This rapid acceleration raises an unavoidable question. What miracles will the next decade hold? Will we see self-sustaining cities built in the vacuum of space, or artificial islands floating in the open ocean? The benchmarks for scale and speed have changed. What was once considered a multi-generational undertaking is now a standard delivery timeline. Let us know in the comments what you think the next great engineering marvel will be, and make sure to subscribe for more deep dives into the projects shaping our world.